Okay, so here is another practice mechanics problem. Box A sits on a horizontal table. A string attached to box A is strung over a pulley and attached to box B, which hangs vertically. Assume there is no friction or drag, and the pulley and string are massless. If the mass of box A is 9 kilograms and the mass of box B is 3 kilograms, find the acceleration of box A and the tension in the string. Okay, so the problem highlights for us what our unknowns are. We need to find the acceleration of that box. We also need to know the tension, right? What is tension? Tension is a force of a string or a rope or a chain on an object. Tension is a pulling force, right? A rope or string can't push, they can only pull. So tension is a pulling force. So our unknowns are a force and an acceleration. So that leads us to our starting point for the problem, right? We have to use our physics conceptual knowledge to figure out how to start the problem. So one of our unknowns is tension, which is a force. There is no equation for tension. It's always an unknown in Newton's laws that we can solve for using Newton's laws. So the fact that tension is an unknown leads us directly to using Newton's laws to solve the problem. Also, to find acceleration, we know that in order to have acceleration, there has to be a net force on something. So again, acceleration is one of the key parts of Newton's laws. So that again leads us, the fact that that is an unknown, leads us to using Newton's laws in our solution. So let's go ahead and think about how we're going to start this. I'm going to write down some of my knowns. I know the mass of box A is 9 kilograms. I know the mass of box B is 3 kilograms. I know there is no friction. Right, one way of writing that down is a coefficient of kinetic friction between box A and the table must be 0. Right, box A is sliding without any resistance. They also tell me that the string is massless and the pulley is massless. Now this is of course unrealistic, but we can assume the string is some very little light piece of string and the pulley is some cheap little plastic light object, so we can basically assume they have no mass. And that is in fact a very important part of solving this problem. The fact that that pulley is massless tells us that the tension is going to be the same in the string everywhere. If the pulley had mass, it would have a moment of inertia. To get it spinning, you would need a net torque, which means the force on one edge must be bigger than the force on the other edge, and the tension would be different in different parts of the string. But since it is a massless pulley with 0 moment of inertia, I'll write that down. That tells us that the tension is going to be the same everywhere in that string. Okay, those are our unknowns. What about our unknowns? Again, we talked about that at the beginning of the problem. Our unknowns are acceleration of box A and tension, which is a force. Now the acceleration of box A is going to be the same in magnitude as the acceleration of box B, because they're connected by a string that's not going to stretch or compress. So I'm just going to call that acceleration and just use A as my symbol for that throughout the problem. And then I'll use the symbol capital T for my tension. Okay, so those are my knowns and unknowns. And again, the concept here is Newton's second law. It's that the sum of the forces acting on any object must be equal to the mass of that object times the acceleration of that object. Right? This is just anything that accelerates must have a net force on it. And I can just tell by looking at these objects there's going to be acceleration, and that's one of our unknowns, of course. But box A definitely has an unbalanced force. It has that force of the string pulling it to the right. There is no force pulling it to the left. It definitely has an unbalanced force. It's definitely a net force. It is definitely going to accelerate. Box B is also has force of gravity down. It has tension up. Those forces must be unbalanced because B is going to fall. It's going to accelerate downwards. And so we can use Newton's laws to solve for unknowns like acceleration and tension. So that's going to be my concept here. Now, how do we actually use this equation? Well, we've got to be careful because forces are vectors, acceleration is a vector, so we have to make sure we define coordinate systems properly. We need to make sure we know which direction is the positive direction and which direction is the negative direction. So to do that, it's very helpful to draw free body diagrams and to define coordinate systems. So that's the next step I'll do. I'm going to draw a free body diagram for each object in my system. So here I have two objects, object A and object B. So for object A, I'm going to draw a dot to represent the center of mass of object A, and I'm going to draw force vectors with their tail starting at that dot for every force acting on A. So I know on A it has a force of gravity acting down. I'm just going to call that the weight of A. I know that it's not falling through the table, so therefore there must be a force up canceling gravity. There must be something balancing the force of gravity down, and so we're going to call that the normal force up on A. You could also call it the force of the table on A. Either one is okay. And then I see there's a string attached to A, and that string is being pulled down by that object B, which is hanging. So there's definitely going to be a tension force, a force of the rope on A to the right. Right? Strings can only pull. So I'm going to call that tension, and that is my free body diagram for A. Now for B, again, we'll draw a dot for B. I'm going to draw all the forces acting on B. So B also has mass, therefore it also has gravity. So it has a force of gravity acting down. I'll call that the weight of B. And then it's not just falling down in free fall. It's not just falling like dropping an object. It has a string attached to it, right, which is slowing down how fast it can fall. So there's also this tension force up. Okay, so the way I drew my free body diagram for B, I can definitely see I have unbalanced forces. Right? I definitely have a net force which is down. My gravity down is bigger than my force of tension up, and therefore I'm definitely going to have acceleration, which is down. Likewise for object A, I could see that to the right there's a tension force, to the left there is no force, so that is definitely an unbalanced force. For A, I definitely have a net force to the right, and therefore I'm definitely going to have acceleration to the right. Okay, so I can tell that from my free body diagrams. Anytime I have those unbalanced forces, I'm going to get acceleration. Okay, but okay, all these vectors I drew are vectors, and again, vectors have components which could be positive or negative in value, and therefore it's really going to be helpful for us to write down these vectors in terms of their components and to recognize when those components are going to be positive numbers and when are they going to be negative numbers. So to do that, I need to define a coordinate system. So for object A, I'll define up to be the positive y direction, and I'll define to the right to be the positive x direction. So that's just a choice I can make. And once I do that, I can recognize which forces have positive vector components and which ones have negative. The normal force is entirely in the plus y direction, right? So it's some vector with a component equal to, I'm going to call it ny for the y component of the normal force, j hat, where j hat is my unit vector that points in the y direction. So that vector is going to be have some component in y and no component in x, right? And so what is that y component? Well, it's definitely going to be positive because it's in the positive direction, and its magnitude is just going to be equal to the magnitude of that vector because that vector entirely points in plus y. So I'm just going to say this is n j hat, right? That entire vector points in the plus y direction. Now let's do the same thing for the weight. The weight is I can see in the minus y direction. So the weight, if I write it as a vector, is going to be something with a y component, j hat. Now what is that y component? That y component must be a negative number, right? This vector points in the negative direction. And what is the magnitude of that vector? Well, it's just all of that vector points in the y direction, right? It has no x component. So if I want to write what is that y component, it's equal to minus the entire magnitude of that vector, j hat. So I know what that vector w is, right? It's definitely something with a negative y component. Similarly, tension must be in the x direction. So it has some x component I hat, and what is that x component? Tension entirely points in the x direction, so it's just going to be the whole tension vector magnitude I hat. Okay, let's do the same thing for B. Now for B, I have to define a coordinate system. I have a choice. I can make the same choice I made before and define up to be the positive direction, but that would cause problems. If I define up to be the positive direction, say positive y, then my acceleration would be negative, but over in my diagram for A, my acceleration is in the positive direction. So that's going to lead to minus sign issues, where the acceleration of A is equal to minus the acceleration of B. That's going to be really messy. So I'm not going to make that choice. It's very helpful just to make everything in your problem move in the same direction, meaning everything, if one object has positive acceleration and it's connected to another object, also make that object have positive acceleration. So I'm going to define down to be the positive y direction for B. Right, that's a choice I can make. Now that I've made that choice, I can see that my weight vector, this vector down right here, is entirely in the plus y direction. So this vector has some y component, j hat, has no x component. And what is that y component? That y component must be a positive number, because this vector points in the positive direction. And the entire vector is in y. So this is just equal to the magnitude of the weight of B, j hat. If I look at the tension acting on B, that's pointing in the minus y direction. So it's definitely going to be some vector component of that tension in y, j hat. But what is that vector component? It's definitely a negative number, right? It's definitely pointing in the negative y direction. So this is going to be minus, and then that, again, the entire vector points in y, so minus the magnitude of my tension, j hat. Okay, so that was a lot of work writing down these free body diagrams. I haven't even thought about how to solve the problem yet, but it's really going to come in handy when we start filling out the next step of this problem. When we start using our concept to figure out what is the net force on each of my objects, these free body diagrams are going to help me figure out that net force. And that's the hardest part of these problems typically. Okay, so now that I have my free body diagrams, I can start applying my concept. I know that each of these objects is going to have a net force on it, which is going to cause acceleration. And therefore, if I use Newton's law to fill in what that net force is, I'm going to get a system of equations that I can use to solve the problem. So for each diagram, I'm going to use Newton's law. So I'm going to write down Newton's second law for object A. The sum of the forces acting on object A is equal to the mass of A times its acceleration. Likewise, the sum of forces acting on B is equal to the mass of B times its acceleration. Right, so we can write down that equation twice, one for each object. Now it's our job to figure out how to plug into this equation. And it's not simple plug and chug. We have to use our free body diagrams to carefully think about what the sum of forces is. So the first thing I'll note is that for this is the vector equation. It's true both in x and y, but I can see for object A, in the y direction, all the forces are just balanced. The weight down is canceled by the normal force up, so that's not going to really help me solve the problem. In the x direction, I am going to have a net force. It's going to cause acceleration, so I'm just going to write this as instead of a vector equation, as a component equation. The sum of the forces acting on A in the x direction must be equal to the mass of A times the acceleration. And that is the acceleration in x, but I'm not going to bother writing that down just to use, because again, everything in the system has the same acceleration. Likewise for B, all the motion is in y. I'm going to turn this from a vector equation into a component of a vector equation. The sum of the forces acting on B in the y direction must be the mass of B times the acceleration of that object in the y direction, which I'm just going to call A, because that is, again, everything in my system I've defined to have the same acceleration. So this is where the free body diagrams come in really handy. I have to figure out, what is this? What is the sum of the forces acting on A in the x direction? Well, I look at the x direction of A's diagram, and I only see one force. It's the tension, right? And this is the sum of the forces acting on A and x, and I see I have a vector that has an x component. That's what I'm going to plug in here. The tension in x is the only force acting on A and x. And that's equal to the mass of A times acceleration. What is the tension in x? Well, that's just, all of the tension, right? Because that vector has no y component. So it must be the case that the tension in the string is equal to the mass of A times the acceleration of that object. Okay, I can't solve the problem yet because I don't know my tension or my acceleration. Those are both unknowns to me. But I have an equation that may be useful. I have two unknowns. I'm going to need two equations. This is the one equation I generated from object A, but let's use object B. For object B, we can generate another equation and hopefully solve for my unknown. So what are the sum of forces acting on B? Well, again, my free body diagram is going to come in really handy here. I have to look at all the forces in Y acting on B. There's weight that has a Y component, and there's tension that has a Y component. So I have to add those together. Right? That's what the sum of forces mean. I'm going to add the weight in Y plus the tension in Y. And the sum of those forces are going to result in acceleration of object B. What are those components? Well, the weight, the weight of B in Y. I'll be careful with that. What is the weight of B in Y? That is just the entire weight vector of B, right? Its whole vector points in the plus Y direction. What about the tension in Y? The tension in Y is in the negative direction, right? The Y component of that vector must be a negative number. So when I add in what is that Y component, I'm adding in minus the tension. And the sum of those two forces give me mass times acceleration. So now I have a system of two equations. I have in each equation tension and acceleration as unknowns. I have mass as a known, and then I have weight, which at the moment is an unknown. They didn't tell me the weight of any object in this problem, but I have an equation for weight, right? We know that weight is equal to mg, so I'm going to be able to figure out what that weight is. So let's do that. Again, I know that the weight of B is equal to just the mass of B times g, minus the tension is equal to the mass of B times A. So indeed, I have these two equations, one from object A, one for object B, that both have two unknowns. So I have two equations, I can use it to solve. And so the best thing to do here is take this tension and just plug it in here. Take the tension equation I generated from A and plug it in for tension in my other equation, and I'll just get rid of tension. So I have the mass of B times g minus, instead of tension, I'm going to have the mass of A times the acceleration equals the mass of B times the acceleration. And this is an equation I can solve. I only have one unknown now, acceleration. I'm going to move that to the other side of the equation by adding the mass of A times the acceleration to both sides of this equation. So I end up getting the mass of B times g is equal to the mass of A times A plus the mass of B times A. Now I can, on the right side of this equation, I can pull out an A. I have A times the mass of A plus the mass of B is equal to the mass of B times g. And now I can divide both sides by the mass of A plus the mass of B, such that on this side it goes away, and I end up solving for the acceleration. So the acceleration must equal the mass of B times g divided by the mass of A plus the mass of B. So I generated an equation for my unknown with everything in this equation is known to me, right? I know the I know the mass of B is 3 kilograms. I know what g is. I know it's 9.81 meters per second squared. For now, I'll just keep it as g. You'll see why in a moment. I know the mass of A is 9 kilograms. I know the mass of B is 3 kilograms. So when I plug in, I get 3 divided by 12, or 1/4. So the acceleration of the system is going to be 1/4 of g, 1/4 g, 0.25 times g. I can now plug in acceleration is equal to what g is, 9.81 meters per second squared, and I can get a numeric answer from my acceleration, which ends up being 2.4525, but I'm going to round to 3 sig figs, so I have 2.45 meters per second squared. That is my acceleration. That's my final answer for one of my unknowns. Okay. Now that I know my acceleration equation, it's pretty easy to find my tension because we generated these equations before for tension. So for example, I could take this equation and just plug into it now. Tension is the mass of A times acceleration. So tension must equal the mass of A. And I'll plug in my equation for acceleration here, times the mass of B times g divided by the mass of A plus the mass of B. So I end up with an equation for tension. It's the mass of A times the mass of B divided by the mass of A plus the mass of B. all times g. So I get a tension equation, and I can now plug in my numbers and solve. Right? It's probably easiest to just, since we already found the acceleration, to just plug into this equation, to be honest. But it will be useful later to have that symbolic equation for tension. So the tension must be equal to the mass of A, which was 9 kilograms, times the acceleration, which we found was 1/4 g. And so when I plug in, I get the tension is equal to 22.0725 newtons, or 22.1 newtons when I round to proper sig figs. Right? Check my units. I know Newton is a kilogram meter per second squared. I have a kilogram times the unit of g, which is a meter per second squared. So indeed I get units of newtons, so that must be my tension. So I have my final answer. So before we move on to the next problem, it's a really nice idea to think about, does this answer make sense? Is it reasonable that my acceleration is 1/4 of g? Is it reasonable that my tension is 22.1 newtons? And think about some extremes that could happen with this. So just to think about this a little further, I am going to quickly rewrite these equations. The acceleration is equal to the mass of b divided by the mass of A plus the mass of b times g. That's what we found for the acceleration. I'm going to write this in a slightly different way in order to take a limit and think about what's the maximum my acceleration could be of the system. What's the minimum of the acceleration I could find? All right, if B, the hanging mass, was really heavy, what's the maximum acceleration I would end up with? Or if the object on the table was really massive, what's the minimum acceleration I could end up with? So to do that, I'm just going to multiply and divide. I'm going to multiply the numerator by 1 over the mass of b, and I'm going to multiply the denominator by 1 over the mass of b. All right, so effectively I'm multiplying my equation by 1. And when I do that, I get my acceleration is equal to 1 over the mass of A plus the mass of B plus 1, all times g. So what was the benefit of doing that? Well, now I can look at this equation and think about my extremes. So I can see that as the mass of A goes to infinity, right? If the object sitting on the table gets to be really heavy, well, this term is going to get really, really big. So my whole denominator is going to go to infinity. If my denominator is going to infinity, then I have 1 over a very large number that's going to be a really small number, right? So my acceleration is going to go to 0. So in that extreme, when I have a really massive object on the table, my acceleration will tend towards 0. Likewise, we can see as the mass of B goes to infinity, well, now I have the mass of A over the mass of B in my denominator there. That term is going to get really tiny, right? That term is going to go to 0 as that mass of B gets really big, which means that term in brackets is just going to head towards 1, right? If this term is going to 0, I just get 1 over 1 times g, so my acceleration ends up being heading towards g. So in the limit of an extremely massive object hanging from this system, the fastest the system can move is g, right? Nothing's going to fall faster than g when the only external force on the system is gravity. So it's good to check that extreme. So the fact that we got an answer of 1/4 of g seems to be pretty reasonable. So because every answer to this problem must be somewhere between 0 and 9.81. And it's helpful to plot this. You can plot the acceleration using this equation as a function of the mass of A, keeping the mass of B constant, and you'll find that if the mass of A is 0, you just have B falling at 9.81 meters per second squared, and the more massive A is, the smaller the acceleration, but it doesn't go down in a linear way. It goes down in a nonlinear way such that it kind of asymptotes towards 0. So if A gets really massive, the acceleration goes to 0. You can also plot this acceleration as a function of the mass of B. So as the hanging mass increases, well, if the hanging mass is 0, then my acceleration is 0 because I just have mass A on that table not being pulled at all. But as my mass of B increases, my acceleration goes up, it goes up and goes up, but it doesn't go up in a linear way. It curves towards some maximum. And what is that maximum? It asymptotes towards 9.81 meters per second squared. So as you get to have a really massive hanging mass, the whole system will just accelerate at 9.81 meters per second squared. You can do the same thing with that tension equation. Let's rewrite that tension equation. Tension is equal to the mass of A times the mass of B divided by the mass of A plus the mass of B. Again, let's just, in order to take a limit, multiply this equation by 1, meaning multiply it by 1 over the mass of A times the mass of B divided by 1 over the mass of A times the mass of B. Right, and doing that, my numerator will cancel out, and I'll get just mass of A and mass of B once in this equation. So I end up with tension is equal to 1 over the mass of B plus 1 over the mass of A. And so this is helpful to think about extremes. Right, so if we fix the mass of A and let the mass of B go to infinity, if the mass of B goes to infinity, then 1 over the mass of B will just go to 0, which means my tension will just go to 1 over the mass of A. I'm sorry, I'm missing a G in this equation. Times G here, so I'll end up with tension just going towards the weight of A. So the mass of A times G, or the weight of A. So if B is extremely heavy, the tension in the system tends to go towards the weight of A. Okay, so let me draw that. I have tension as a function of the mass of B, holding the mass of A constant, and you'll find that the tension tends to go up and up and up in a nonlinear way such that it asymptotes towards the weight of A. Okay, so that's interesting. So the tension in the rope will be 0 if the mass of B is 0, if the hanging mass is 0. But as the hanging mass gets bigger and bigger, the tension goes up, but it's not going to keep going up. It goes up to the weight of A. And let's also check what happens as the mass of the mass of A goes to infinity, keeping the mass of B constant. As the mass of A goes to infinity, again, the same thing will happen. 1 over the mass of A will go to 0. Tension will go to 1 over the mass of B times G, or the mass of B times G, or the weight of the weight of B. Okay, so if you have an extremely massive object on the table and just a hanging mass, well, the tension in that system is just going to be the weight of the hanging mass. So let me draw that real quick. Again, if we plot this equation, the tension as a function of the mass of A, keeping the mass of B constant, the tension will be 0 if there is no mass on top of the table. As that mass gets more massive, the tension goes up and up and up. It's kind of more inertia. There's more for the system to move as the thing on the table gets more massive. The tension goes up, and but it doesn't go up forever. In the limit of the mass of A getting really heavy, it's kind of as if that rope was just tied to the wall, and the tension goes up to the weight of A. So no matter what, the tension in that cable, for any, if you do this problem in a lab or something like that, the tension in that rope is always going to be less than the weight, right? It has to be. And so that's an interesting problem. So it's good to think about kind of the extremes of your answer just to make sure that your answer makes sense. So on to the next problem.